Assalamu alaikum. Hi everyone. In this video, I would like to explain the attributes of the flip-flop that makes them become very useful to be used in the realization of a finite state machine. By the way, I'm not intending to describe the architecture of the flip-flop devices in detail. Instead, I'm going to review the characteristics of flip-flop devices and relate those characteristics with the application in finite state machine. Okay, let's begin with the review on the flip-flops. In this regard, I'm going to address three types of flip-flop, perhaps the three most popular flip-flops, namely the JK, D, and T flip-flops. So here are the symbol of these flip-flops, JK, D, and T. Apart from the clock and perhaps the reset button, a flip-flop can have one or two inputs. As an example, JK flip-flop has obviously two inputs, which is J and K. Okay, from the finite state machine points of view, the outputs of a flip-flop is called the states. So this is the states, and normally it comes with its complement, which is indicated by Q bar. So the operation of a flip-flop type is determined by its characteristic equations. So as for the JK flip-flop, its characteristic equation is Q plus. So Q plus in here indicates the next state, equals to J Q bar or K bar Q. So Q on the right hand side is the present state, corresponds to the present state, and Q plus on the left hand side corresponds to the next state. Next, for the D flip-flop, the next state Q plus simply equals to D. And for the T flip-flop, Q plus equals to T XOR Q. So the D flip-flop is perhaps the most straightforward. For example, if D equals to 1, the value of the states in the next clock cycle is also 1, because Q plus equals to D. And for the T flip-flop, this equation can be interpreted as if T 0, the next state keep the value of the present state, and if T is 1, the value of the next state is Q bar or toggle. We call toggle. Alright, so in all flip-flop types, although the next state is the subject of the equation, as can be seen here, Q plus is placed on the left hand side of the equation. So even though Q plus is the subject of the equation, in most cases the problem is not the formulation of the next state, but it's rather how to formulate the inputs of the flip-flops so that the desired next state can be achieved. Okay, so it is about what are J and K, and what is D, and what is T to achieve Q plus. Alright, so based on these characteristic equations, we can derive the two types of table. So namely the characteristic table and the excitation table. So the characteristic table is directly obtained from the equation. As for example, if you refer to the first line, it's simply like substituting J0 and K0 into the right hand side of the equation, and we obtain the Q plus. So you can try to do line by line to prove this value, and so with the D and T flip-flop. By the way, the D flip-flop is perhaps, as I mentioned just now, is the most straightforward, so nothing much to do with the proof. And secondly, we have the excitation table. So the excitation table and the characteristic tables, in fact, they are equivalent. But the excitation table is something like looking the circuit from another perspective. So alright, this is how to read the excitation table. Let's follow the first line of the excitation table of the JK flip-flop. Here, if the present state is 0 and the desired next state is also 0, so we must set J0, and it doesn't matter with the value of K, or we call it as don't care. So the following line is like, if the present state is 0 and the desired next state is 1, we must set J1 and K don't care, and so on. So again, the problem is how to formulate the input of the flip-flop based on the desired next state, because the desired next state is already known based on the sequence of a particular system or machines. As an example, if a counter is counting up, so we know that if the present number is number 5, so the next number should be number 6, and then number 7, and so on. Or another example, if a counter is counting the even numbers, so we know that the sequence should be 0, 2, 4, 6, and so on. Or let's take a traffic light system. So we know that after a certain time duration of the green light, the yellow light should come, for example, for a 3-second time duration, and followed by the red light. So to conclude this video, I would like to re-emphasize that the desired next state is already known according to the specification of the system. Thus, the main problem is how to formulate the inputs of the flip-flop to achieve the next state that can complete the sequence.